Piping vibration, specialist predictive techniques, advanced methods for accurate data forecasting and analysis. This presentation refers to guidelines for the avoidance of vibration-induced fatigue failure in process pipework by Energy Institute. Overview of specialist predictive techniques. Specialist predictive techniques are advanced analytical methods used to assess piping excitation and response in industrial systems. These techniques are particularly valuable during the design phase when potential vibration issues are identified through quantitative likelihood of failure (LOF) assessments, or during troubleshooting of known vibration problems. Their primary purpose is to provide detailed insights into dynamic behaviors and to evaluate the theoretical effectiveness of corrective actions before implementation. The techniques encompass structural and acoustic finite element analysis, computational fluid dynamics, CFD, pulsation analysis, surge analysis, and valve sizing calculations. Each method addresses specific excitation mechanisms such as flow-induced turbulence, mechanical excitation, pulsation from reciprocating or positive displacement pumps and compressors, rotating stall, high-frequency acoustic excitation, surge due to valve operations, and cavitation or flashing. By applying these predictive tools, engineers can simulate complex interactions between fluid and structure, predict natural frequencies, mode shapes, and dynamic pressures, and ultimately design safer and more reliable piping systems. These techniques also help in mitigating risks associated with vibration-induced fatigue, noise, and operational inefficiencies, ensuring compliance with industry standards and improving overall plant reliability. Principles and applications of structural finite element analysis. Structural finite element analysis, FEA, is a widely used technique for predicting the dynamic response of piping systems and components. It enables engineers to determine free vibration characteristics such as natural frequencies and mode shapes, as well as steady-state and transient forced vibration amplitudes including displacements, velocities, accelerations, and stresses. The modeling approach varies depending on the application. For low-frequency flexural modes, 3D beam elements or pipe elements derived from beam elements are suitable. For high-frequency shell modes, 8-node shell elements are recommended, and for complex components like strain-based components, SBC, a combination of shell and solid brick elements is required. Accuracy in predictions depends on factors such as mass distribution, including insulation, contained fluid, and lumped masses like valves, stiffness of the pipe and supports, and representation of support arrangements. Dynamic behavior of supports often differs from static assumptions, as supports and connected structures may flex, reducing natural frequencies. Additionally, frictional effects in guided supports can restrain dynamic movement even when static thermal growth is allowed. Estimating dynamic force levels and structural damping, typically between 1 to 2% of critical, is essential for accurate forced response predictions. Experimental modal analysis can further refine damping estimates for specific configurations. Dynamic fluid response prediction, acoustic finite element analysis. Acoustic finite element analysis focuses on predicting the dynamic response of fluids contained within piping systems and associated volumes such as vessels. This technique allows for the determination of modal characteristics, including natural frequencies and mode shapes, as well as steady-state and transient response levels like dynamic pressures and associated forces. Acoustic FEA is particularly effective for analyzing both low and high-frequency modal behavior, as it can capture axial and cross modes depending on mesh density. This capability makes it superior for comprehensive modeling of fluid dynamics compared to simpler methods. By simulating acoustic behavior, engineers can identify potential resonance conditions, pressure pulsations, and force distributions that may lead to vibration issues. These insights are critical for designing piping systems that minimize acoustic-induced stresses and prevent operational problems such as noise, fatigue, and component failure. Acoustic FEA also supports troubleshooting by pinpointing sources of abnormal pressure fluctuations and validating corrective measures before implementation. Flow pattern analysis and vibration insights, computational fluid dynamics. Computational fluid dynamics, CFD, is a powerful modeling technique used to predict flow patterns within piping systems and associated components such as valves and orifice plates. By simulating fluid behavior under various operating conditions, CFD provides detailed insights into flow-induced phenomena that can contribute to vibration problems. These include turbulence, pressure drops, and localized flow disturbances that may excite structural components. CFD models help engineers visualize complex interactions between fluid and structure, enabling the identification of regions prone to high vibration or noise. This predictive capability is essential for optimizing component design, improving flow distribution, and mitigating risks associated with fatigue and operational inefficiencies. CFD also supports troubleshooting by revealing root causes of vibration issues, such as improper valve sizing or unexpected flow separation. Ultimately, CFD enhances system reliability by informing design decisions that reduce vibration-related failures and improve overall performance. Pulsation analysis and surge prediction. Pulsation analysis involves acoustic simulation of the fluid within a piping system to predict natural frequencies and mode shapes. It also estimates the forced response of the fluid to excitations from reciprocating or positive displacement compressors and pumps, as well as flow-induced pulsations. Typically performed using transfer matrix methods, pulsation analysis is effective for modeling piping components such as valves and orifice plates and accounting for acoustic damping due to fluid flow. However, it is limited to plane wave transmission and cannot predict cross-mode behavior, unlike acoustic FEA. Surge analysis, on the other hand, focuses on transient flow events such as sudden valve closures or pump startup/shutdown. Conducted in the time domain, surge analysis predicts dynamic pressures and forces as functions of time, providing insights into potential pressure spikes and structural loads. These analyses are critical for designing control systems and protective measures that prevent damage from transient events, ensuring operational safety and reliability. Ensuring valve suitability. Valve sizing calculations are essential for determining the suitability of valves in piping systems, particularly concerning flashing and cavitation risks. Improper valve sizing can lead to severe operational issues, including vibration, noise, and component damage. Comprehensive calculations consider factors such as fluid properties, pressure drops, flow rates, and system dynamics to ensure valves operate within safe limits. By accurately sizing valves, engineers can prevent conditions that cause rapid phase changes in the fluid, which often result in cavitation and flashing. These phenomena not only degrade valve performance but also generate high-frequency vibrations that can propagate through the piping system, leading to fatigue and failure. Valve sizing calculations thus play a crucial role in maintaining system integrity, optimizing performance, and reducing maintenance costs.